Hello, and welcome to our module on acids and bases. This is an introductory module where we'll cover what an acid and a base actually is, and the difference between strong and weak acids and bases. So what actually is an acid? Typically, an acid is anything below a neutral pH, or a pH of 7. Some commonly known acids that you need to know for your exams are acetic acid, which is found in vinegar, and hydrochloric acid, which is found in your stomach. We use hydrochloric acid to digest food and also activate digestive enzymes. There are many models for the definition of an acid. The most common one, or the one that you need to know the most, is the Bronsted-Lowry model, which describes an acid as a proton donor. A proton in this context is equivalent to H+, and if you think about it, they're kind of the same thing. So H+ is hydrogen without an electron, which is the same as a proton. So Bronsted-Lowry acid is a proton donor. Acids can be monoprotic, meaning they can give one proton, or polyprotic, meaning they can give multiple protons. Now we'll go through a worked example of an acid dissolving in water. So as I previously stated, an acid, or anything that is acidic, is below a pH of 7. Stronger acids tend to be further away from 7, and weaker acids tend to be closer to 7. Here we have hydrochloric acid dissolving in water. Pause the video and figure out what's going on. So basically, the H from hydrochloric acid is binding with the water here. In this way, hydrochloric acid acts as a proton donor. This yields H3O+, which is nothing but H2O with an extra H+ bonded. This and H+ are used interchangeably because they do mean the same thing. The chloride forms an anion in solution. In this way, HCl dissociates into a negative ion and hydronium. Now it's important to distinguish between a monoprotic and a polyprotic acid. For a monoprotic acid, we'll use HCl as an example again. For every 1 mole of HCl, we get 1 mole of hydronium or H+. This is a bit different to sulfuric acid, which is a polyprotic acid. Poly meaning many and protic meaning proton. Sulfuric acid actually dissolves in a 2-step equation. The first step yields a hydronium. The second step yields another one. So in this way, for every 1 molecule of sulfuric acid, you get 2 moles of hydronium. In this way, sulfuric acid is a polyprotic acid. Now that you've understood how acids dissolve in water and the difference between a monoprotic and a polyprotic acid, an important relationship that you need to understand for your exams is the difference between a strong acid and a weak acid. For consistency's sake, we'll use hydrochloric acid as our example for a strong acid. So obviously the acid would be HCl. The proton would be H+, which is also the same as H3O+, and the negative ion would be chloride. Compare the strong acid beaker to the weak acid beaker. The strong acid beaker, when put in solution, likes to break up into the individual proton and the negative ion a lot better than the weak acid, which kind of stays intact. A nice way of putting this is, a strong acid dissolves or dissociates into a proton and a negative ion a lot better than a weak acid, which doesn't tend to do that. For your exams, it's very high yield to know the difference between strong and weak acids and some examples for each. Hydrochloric acid, nitric acid, sulfuric acid are the main ones you're going to see for strong acids. For weak acids, it's mainly going to be acetic acid, and maybe cyanic acid. Now that we've covered what an acid is, it's time to cover what a base is. Typically, anything above a neutral pH or a pH of 7 is classified as basic. The Bronsted-Lowry model describes a base as a proton acceptor. So an acid is a proton donor, so it likes giving protons. A base is a proton acceptor, so it likes accepting protons. An example of a base is sodium bicarbonate, which we use as a medication to neutralize stomach acid, especially in reflux. As I previously stated, a base is anything above a neutral pH. Stronger bases tend to be further from 7, and weaker bases tend to be above 7 or just above 7. Now we'll go through an example of a base, sodium hydroxide in this case, dissolving in water. Take a minute to pause the video and work out what's happening. In this instance, water dissociates and gives a H plus to sodium hydroxide. This H plus combines with the hydroxide group and gives you water. We don't really bother writing this water because it's in an aqueous solution, aqueous meaning in water, but this yields a sodium that we carry across and a hydroxide which is left over from the H2O. So H2O, if we take over a H, we have OH minus. In this way, sodium hydroxide dissolves into sodium and a hydroxide ion. Now that you've looked at how an acid and a base dissolve in water, and what a Bronsted-Lowry acid and a Bronsted-Lowry base is, I have a more complex example. This is acetic acid and an organic base. Take the moment to pause the video and work out which is acting as a Bronsted-Lowry acid and which is acting as a Bronsted-Lowry base. As you can see, the acetic acid donates a H plus to the organic base to make it CH3NH3 instead of NH2. Thus, acetic acid here donates a proton to the organic base. Thus, it's a Bronsted-Lowry acid, and since the base accepts the proton, it's a Bronsted-Lowry base. Like strong and weak acids, you can also have strong and weak bases. The same concept applies in that strong bases really like dissociating into their ions in solution, whilst weak bases really don't like dissociating into their ions in solutions. Some examples of strong bases include your alkali earth metals with a hydroxide ion. So lithium hydroxide, sodium hydroxide, and potassium hydroxide. Some examples of weak bases include ammonia and sodium bicarbonate. A very high order association that you need to remember, especially moving forward, is that water can act both as a weak acid and a base. If I turn your attention to this page, water is donating a proton, so it's actually acting as a Bronsted-Lowry acid. However here, it's accepting a proton, and thus acting as a Bronsted-Lowry base. Thus, in this way, water can act both as a weak acid and a weak base. Electrical conductivity, simply put, is just the movement of ions. Thus, both acids and bases in solution can conduct electricity. It should be no surprise to you that strong acids and bases are better conductors of electricity than weak acids and bases. This is because strong acid and strong bases tend to dissociate into their ions a lot more than weak acids and bases. Thus you have more ions in solution, thus more ions able to move, thus better electrical conductivity. This is a diagram summarizing today's module.